Let's do some more quotient rule practice and see some places where you might need some advice. So here's a fraction, a rational expression. Go ahead and take the derivative of it using the quotient rule. Pause the video while you do that. All right. Hopefully you wrote out the beginning of the generic form low d high minus high d low over square of the bottom, which you could just write as g squared or low squared, whatever. All right, so what is low here? It's 9t plus 23. D high would be 3t plus 11 prime minus high, that's 3t plus 11 times d low, which is 9t plus 23 prime over 9t plus 23 squared, right, g squared. So what do you think of the work I just did? Feel free to criticize me. What did you notice? All these additions need to be protected from multiplications and derivatives, not protected from derivatives, but we need to make sure the derivative happens to everything that it should happen to. So I should have put parentheses around that, parentheses around that, parentheses around that, around that, around that, and around that. We really need all those parentheses. All right. Let's try another common derivative. What is the derivative of tangent theta? Well, do you know what tangent theta is equal to? Maybe that makes life easier. Well, it's sine theta over cosine theta. Now can you take the tangent of theta? Well, we just learned the quotient rule, so go ahead and do the quotient rule. Pause the video while you do that. Okay, welcome back. Let's see, we want low d high minus high d low over low squared. So that would be cosine theta times sine theta squared minus high is sine theta, d low is cosine theta prime over cosine theta squared. Okay, so far? I think it's good. Oh, except I took a squared here and it should have been a prime. There we go. Okay, so hopefully you got to that point. And then the next step, you have cosine theta. What's the derivative of sine theta? It's again cosine theta minus sine theta. And what's the derivative of cosine theta? It's minus sine theta over cosine theta squared. Looking good so far? Notice any trouble? Yep, you caught me. I tried to sneak by without parentheses. I need to put parentheses around that. Otherwise, it's a subtraction rather than a multiplication. It really should be a multiplication. Or I could have put a dot in between the sine theta and the negative sine theta. All right. So in this one, it helps to simplify here because that's a lot to write out. So we're getting cosine theta squared minus, what we've got two minuses, plus sine theta squared over cosine theta squared. And you might remember that sine squared plus cosine squared equals 1. So you can write this as 1 over cosine theta squared. Perfectly good answer. You could also write it as 1 over cosine theta as a fraction and square that. And you might remember that there's a special term for 1 over cosine theta that is secant theta squared. Is that related to secant lines, like almost like tangent lines? It turns out it is in a really kind of convoluted way that we don't need to worry about. So people like to say that the derivative of tangent is secant squared. Notice this is a squared, it's not a prime. Derivative of tangent is secant squared, but it's also not wrong to think of it as 1 over cosine squared. Okay, let's do one more quotient rule kind of problem. Let's do 14 e to the t over 100 prime. All right, so go ahead and do the quotient rule. That would be low d high minus high d low, square the bottom. All right, so low is 100, d high would be 14 e to the t prime, high is 14 e to the t, d low would be 100 prime over 100 squared. Okay, so far? And how about simplifying that? Well, 100, what is 14 e to the t? Do I need the product rule there? That's a product of two terms. Oh, I hope I don't need the product rule. Ah, but it's a constant multiplier. The 14 is a constant vertical multiplier, so I don't need the product rule. I can just use the constant multiplier rule. So that'll just be the 14 derivative of e to the t is e to the t. Can you imagine if I had had to do the product rule right there? I would have had all these parentheses and stuff. And that could have happened if this was like a sine t e to the t. But boy, did I just save myself a big headache by noticing that I didn't need the product rule right there. All right, and then 14 e to the t. And what's the derivative of 100? It's 0. 100 is a constant, so I get times 0. And then divide by 100 squared. And what's happening here? That second term just went away entirely. And well, I have 100 over 100 squared. I can simplify that. I kind of cross out the squared and cross out the 100, and I just get 14 e to the t over 100. So all that quotient rule stuff, I got something fairly simple. Do you notice anything that I might have done differently here? Well, I could have rewritten this or thought about it as 14 over 100 e to the t prime. Or I could have thought about it as 14 times 1/100th e to the t prime, moving the 14 out because of the constant multiplier rule. So this is a ratio. I might use the a quotient. I could use the quotient rule on it, but it's also a constant vertical multiplier. So I can just write 14 times 1/100, 1 over 100 times e to the t prime. E to the t prime is just e to the t. So I'm getting 14 over 100 e to the t, which I could also write as 14 e to the t over 100. Either way is fine. So did I need the quotient rule on this? It worked out. I got the same answer either way, but which one is better? This one saves a lot of time and you're much less likely to make mistakes. So you should really practice not using the quotient rule if you don't need to use the quotient rule. So let's say this is the via the constant vertical multiplier rule. So let's write again that this is much better So you should really practice not using the quotient rule if you don't need the quotient rule. See how much time it saves you, and you'd have to remember that the derivative of a constant is 0, which usually you remember, but in the midst of a big quotient rule problem you might forget, and then doing the cancellation and everything. So really try spotting when what I'm doing is either multiplying or dividing by a constant, and then you can use this rule. Saves a lot of time and trouble.